Swayam Prabha. Digital India. Educated India.
Learning outcomes are similar as per an earlier session. Only examples are different in this session. Now let's see the contents of this session. IUPAC nomenclature of anthracene and phenanthrene. So in the earlier session we have completed 3 examples from polynuclear aromatic hydrocarbons. So one was naphthalene, second one was diphenylmethane, and third one was triphenylmethane. Now in this session we will be going through anthracene and phenanthrene. So these are the last 2 examples from polynuclear aromatic hydrocarbon as per the syllabus. After that we will see the reactivity of anthracene and phenanthrene. So whenever substitution happens or elimination happens, it is at a particular carbon, and why that carbon is reactive in case of an anthracene and phenanthrene we will look at. After that, synthesis method of anthracene and phenanthrene, reactions of anthracene and phenanthrene, and lastly uses of anthracene and phenanthrene. So anthracene and phenanthrene, they are having quite similar structures, but only if you remember in the earlier session we have seen the classification of fused benzoidal type of structures. So both the examples, they are distinguishing from a category that is from in a fuse, that is one was linear and second one was angular. And anthracene, it comes under category of a linear type of an polynuclear aromatic hydrocarbon fused, and anthracene, it comes in an angular type of an category. So the number of carbon, number of hydrogens, both are similar in the both structures, but only the arrangement of an ring, it is a little bit different in both the structures. So we will look one by one class. Firstly, anthracene and its derivative. Anthracene is tricyclic aromatic hydrocarbon which is linear. In earlier session we have seen naphthalene. So naphthalene was bicyclic, and only the difference between anthracene and naphthalene, it is anthracene is tricyclic and naphthalene is bicyclic, and both things are similar, that is both are linear in nature. So this is a numbering for an anthracene. So it starts from in this alpha position, and second one beta position, and third one gamma. So we are restricted only most of the time to alpha and beta only. So starting from an alpha up to 4 carbon, and after that leaving behind this second ring, going towards third ring, that is 5th, 6th, 7th, 8th, 9th and 10th. So this is a numbering given by an IUPAC. Bromine, it is substituted at 9th position, so it is 9-bromoanthracene. Sulfonic acid, it has been substituted at 2nd position, so 2-anthracene sulfonic acid. After that, nitro, it has been substituted at 9 and 10th position, so di referring to 2 nitrogens, 2 nitro groups, and so di-nitroanthracene. And one more example, that is 9,10 anthraquinone. So hydrogen, it has been replaced, or it has been ring, it has been oxidized to ketone, and there are 2 ketones. So at the last it is said to be an one, and numbering, it refers at 9th and 10th position carbon, they are having one, means they are having an ketone. So remaining structure, it is anthracene. Now we'll come towards an reactivity of an anthracene. Anthracene is more reactive and has greater tendency to add 9 and 10 position, that to substituted. However, the nitration and halogenation readily undergoes elimination to form 9 substitution product. So in case of a nitration and halogenation, so 9th position, it is most reactive, because this it has been surrounded by 2 rings, and it helps So anthracene, when it is brominated or when it has been halogenated, so it forms di type of an product. So double bond, it has been double bond, or we can say pi bond. Now it is broken and it forms a sigma bond further for an bromine by giving away an electron towards an bromine. So this is also an electrophilic aromatic substitution, because the plus part of bromine, it does react with a carbon at 9th position, and is similar in case of an 10th type of an 10th carbon, that plus part of an bromine, it reacts with this pi bond, and after breaking of an pi bond, it forms one more new sigma bond. But as soon as it has been heated, so after heating, one bromine it has been lost, and one more hydrogen from this bromine from ninth position. So it is also been removed after heating, and again it forms an pi bond by losing electron towards an carbon. Here also similar thing happens. It loses an electron towards a carbon and it forms an 9-bromoanthracene. So in case of a reactivity of an anthracene, 9 position, it is one of the most favorable position for any type of an substitution product, because it has a higher reactivity as compared to another carbon, because it has been it is in central position, and this carbocation forming at an central position, so it is quite stable compared to other carbocation at other positions. In some cases we can see also substitution at 1 or 2 position or 3 position, so it depends on a drastic condition, how conditions we are utilizing, but most often we can see substitution at 9th position and readily at 10th position also. Synthesis of an anthracene. So first one, that is Haworth synthesis. So in most of the polynuclear aromatic hydrocarbon, we have seen this kind of an synthesis, that is Haworth synthesis. Benzene is treated with phthalic anhydride and aluminium chloride to form orthobenzoyl benzoic acid. On heating with concentrated sulfuric acid dehydrated to 910 anthraquinone, which on distillation with zinc dust is reduced to anthracene. So we will see the reaction scheme. So benzene reacted with an phthalic anhydride. So such kind of a reaction, it is nothing but an Friedel-Crafts type of a reaction. So whenever Lewis acid AlCl3 comes, so it is nothing but an Friedel-Crafts type of a reaction, and it forms an cyclic product, that is orthobenzoyl benzoic acid. And after heating with sulfuric acid, so water, it has been eliminated and it forms an oxidized product, that is 910 anthraquinone. And after distilling with zinc dust, so it is reduced to our desired product, that is anthracene. So when such reaction it has been carried out, whenever it comes to an Friedel-Crafts type of a reaction at the starting phase, so this reaction conditions are little bit different than another ordinary reactions, because whenever we are utilizing AlCl3 Lewis acid, so Lewis acid, when it comes in contact with a moisture, it destabilizes or reactivity of that AlCl3, forming an hydroxide ion with an aluminium. So reactivity of an AlCl3 it loses. So anhydrous AlCl3 is important for this reaction. So conditions are maintained anhydrous by utilizing different type of an reaction conditions, such as a guard tube, it has been utilized containing an calcium chloride at condenser end, or balloons of some gases which are inert in nature like argon. So they are being utilized because these gases replaces air present in a reaction or the condenser or RBF, and this replacement of an air is been occupied by this some gases, inert gases, and due to inertness there is no moisture, and as there is no moisture, so the yield of product increases. So sometimes it happens that due to moisture condition, or when we are not aligned with an condition of an reaction as needed, we will get very less yield, or sometimes it is we does not get a desired product. So this is a crucial stage to obtain a higher yield, to demoisturize it, or to maintain the dry conditions for a reaction. Next method, that is Ilbis synthesis. The conversion of diaryl ketone containing a methyl or methylene groups ortho to carbonyl functional group is known as Ilbis synthesis. When orthomethylbenzophenone is heated at 450 degrees Celsius, anthracene is formed. So this is structure of an orthomethylbenzophenone. So benzophenone, the one is phenyl ring and second one is an benzyl ring. Phenyl ring means it does not contain any carbon in front, just it is having a bond for an attachment. So up to here the structure it is said to be an phenyl, and when it is benzyl, benzene is different and benzyl is different. Benzene it is restricted to only an aromatic ring, but when it is having one bond, so it is said to be an phenyl. And when this phenyl it is having one more carbon, it is said to be an benzyl. And here you can see that benzene it is not an hydrocarbon, so it is an carboxycarbon, or we can say it is an ketonic carbon, and that is why it is said to be an one at the last. One it refers to an ketone, and the position of an methyl group on benzyl on benzyl ring it is at an ortho position, so it is said to be an ortho methyl benzophenone. When it is been heated at 450 degrees Celsius, it forms an anthracene. So it is just a simple reaction of an cyclization. After that, nitration of an anthracene. So for nitration, we require nitric acid and sulfuric acid as a nitrating agent. So when treated with concentrated nitric acid in acetic anhydride, anthracene forms 9-nitroanthracene and 9,10-dinitroanthracene. So we get two products over here. So reactivity at 9, 10, 10th position, it is quite higher, and that is why we get 9 product and as well as a 9 and 10 product also. So similar can be happen in case of an halogenation, that by using optimal conditions of an reaction we can get dihalide type of an product. As we have got over here dinitro type of an product. So similarly we can also obtain in case of an halogenation. So this reaction, it is carried out in acetic anhydride. After that, sulfonation. Sulfonation of an anthracene with concentrated sulfuric acid at low temperature gives 1 anthracene sulfonic acid, and at high temperature gives 2 anthracene sulfonic acid. So as discussed earlier, beyond the 9th and 10th position, we can also get alpha type of an substitution or beta type of an substitution. So this is nothing but an alpha type of an substitution, that we get first substitution at an first position, that is anthracene sulfonic acid at low temperature, and when it comes to an high temperature, so it is 2 anthracene sulfonic acid, and it has been substituted at an beta carbon. So beta carbon, it requires some drastic condition as compared to an alpha carbon, as we have seen in case of an reactivity of an naphthalene. So alpha, it is having more cationic resonating structures, but beta just have only one cationic, or has only one cationic structure. So we get a drastic condition and beta product. Reactions of anthracene. Next reaction, that is oxidation of anthracene. Oxidation of an anthracene with sodium dichromate and sulfuric acid yields 9,10 anthraquinone. As we have seen, 9 and 10 position, though they are active, and reactivity at 9 and 10 position compared to an other positions is quite higher due to stable carbocation formations. And 9 and 10th carbon, it has been oxidized by removing hydrogens, and it forms an anthraquinone at 9, 10th position. Reactions of an anthracene, that is, now it is a reduction. On reduction with sodium and ethanol, or on catalytic hydrogenation, anthracene forms 9,10 dihydroanthracene. So both the methods can be utilized, and both the methods are giving similar kind of an product, that is 9,10 dihydroanthracene. So one of an product, that is sodium in ethanol, giving a nascent hydrogens, and this nascent hydrogens, they are been substituted or added, not substituted, added by breaking the pi bond, converted to a sigma bond, and after that hydrogen gas by using of an padallium catalyst. So such kind of an reaction, it is said to be an catalytic hydrogenation. Catalytic hydrogenation, it is conducted in high pressure vessel. Hydrogen gas, it is introduced with the use of some solvent in which anthracene, it has been dissolved, and padallium as a catalyst. So it does not get dissolved with an anthracene, it just acts as mediator or catalyst for an adsorption of an hydrogen gas, and again desorption of an hydrogen gas into a molecule. So starting from in 1, 2, 3, 4. So leaving the middle ring behind, 5, 6, 7, 8, and now coming towards the middle ring, that is 9 and 10. So similar as we have seen in case of an anthracene, so phenanthrene is also having a similar type of an numbering, that middle ring uh, Reactivity of phenanthrene. 9 and 10 bond in phenanthrene are quite reactive, in fact almost reactive as alkene double bond. Addition therefore occurs fairly readily. Halogenation can give both 9 and 10 and non-substitution product by following scheme. Phenanthrene after halogenation, so it can give 9,10 dichloro dihydrophenanthrene, and after heating, so HCl, it is removed and it forms an only one type of an halogenated product, that is 9-chlorophenanthrene. And now question comes to in mind, why this 9 and 10 position, they are most favorable for reactivity rather than alpha beta positions or 1 2 position or any other position on the ring. The reason behind is that whenever the carbocations are being formed, so these carbocations are having lot many resonating structure compared to an other carbons, and this is why 9 and 10th position, it is quite reactive compared to an other positions. So in case of an phenanthrene, you can come across some product at alpha and beta also position, but most of the time and easily we can get a product at 9 and 10th position, and in that 9th position it is most favorable for an substitution, and we can get an 9 substituted product. So reactivity at 9th and 10th position, resonating structures are important. So as many resonating structures does we get, so that much the stability increases. So it depends on resonating structure once it forms an carbocation. And whenever any type of substitution it does happen on phenanthrene or any polynuclear aromatic hydrocarbons, so all they are aromatic electrophilic substitution type. So all in case of in each and every reaction, you can see that is electrophilic type of an substitution, electrophilic aromatic. Now synthesis of an phenanthrene. Haworth synthesis, one of an important class, that in almost all the type of an polynuclear aromatic hydrocarbons we have gone through such kind of an synthesis. Naphthalene reacts with succinic anhydride, and such kind of a reaction, it is nothing but Friedel-Crafts type of a reaction and gives a substituted product. And after that, reduction with zinc and HCl, so carbonyl carbon or keto carbon, it has been reduced to alkane, and after addition of an H2SO4 having an acidic media, so this linear acidic chain propyl acid, so it gets cyclized, and after heating it gets cyclized and it forms a partial structure of an phenanthrene. After reduction, the carbon over here, the ketonic carbon, it has been reduced, and by using selenium, of an phenanthrene, halogenation. Phenanthrene reacts with chlorine in carbon tetrachloride at room temperature to give 9,10-dichloro, 9,10-dihydrophenanthrene, an addition product. On heating, this loses a molecule of hydrogen chloride to yield 9-chlorophenanthrene, a substitution product. So whatever we have seen in case of an reactivity, so similar kind of a reaction, that chlorine, it has been reacted with phenanthrene, or halogenation of an phenanthrene takes place in presence of an carbon tetrachloride, and we get a dye product. And after heating that dye product, we can further modify it to an only and mono substitution type of end product, that is 9-chlorophenanthrene. If we require this 9,10-dichloro, 9,10-dihydrophenanthrene, so it can be isolated. Just don't heat it and we will get that molecule after halogenation. But this one last mono substituted product, it is quite stable, and that is why we just are desired to get a 9 substituted product with an nitration of phenanthrene. Phenanthrene undergoes nitration with concentrated nitric acid and sulfuric acid to yield 9-nitrophenanthrene, one of the simple reaction. Nitrating mixture, that is HNO3 and H2SO4. If we are not adding H2SO4, nitronium ion, it is not generated. To generate a nitronium ion, we require sulfuric acid, and we get 9-nitrophenanthrene. Reaction of phenanthrene, further reaction, that is reduction of phenanthrene. Phenanthrene undergoes reduction with sodium and ethanol, gives 9,10-dihydrophenanthrene. So one of a simple reaction, just heat with sodium and ethanol and we get 9,10-dihydrophenanthrene. So dihydro, it refers to that hydrogen, it has been added at 9th and 10th position instead of double bond. So double bond, it has been clashed, or it has been utilized by an hydrogen for addition. The pi bond breaks over here and it forms one more new sigma bond with the carbon, and it is having CH2 and CH2 bridge over here, and so it is said to be 9,10 dihydro at 9th position and 10th position. Reaction of an phenanthrene, that is oxidation. Phenanthrene is oxidized by sodium dichromate and sulfuric acid, which gives 9,10-phenanthrequinone. Sodium dichromate and sulfuric acid, and again 9th and 10th position, it has been oxidized, giving phenanthrequinone at 9th and 10th position. Now we'll see the uses of an phenanthrene. Phenanthrene can produce phenanthrequinone, polyester resin, alkaloid resin, benzene anhydrides. Phenanthrene in paper making, it is anti-fogging agent of a pulp. Phenanthrene in medicine, it can produce alkaloid. So if you remember in pharmacognosy, again you will understand that class from an alkaloid one of a class, that is phenanthrene, and there are lot many alkaloid type of an phenanthrene ring which has been substituted by a different molecule, and this different molecule gives a different activity. Phenanthrene is used in production of fuel of jet plane. Almost all the type of an hydrocarbons, they are used for the preparation of an petroleum, and one of an derivative, that is phenanthrene of an polynuclear aromatic hydrocarbon, it is used for fuel jet. Phenanthrene is naturally found in compounds such as bile acids, sex hormone, morphine alkaloids, and cholesterol. So if you remember the structures of morphine and some alkaloids and cholesterol, so all they are having a basing ring of an phenanthrene, and these are quite complicated structures of an steroid. Now we'll see the summary of this session. So we have seen two position or 10th position. After that, we have seen nitration. In case of a nitration, we get dimers, that is one with a mono substitution at 9th position and second at 10th position, 9 and 10, and this reaction is carried out in acetic anhydride. After that, we have seen sulfonation. So sulfonation, they are done at different temperatures. So at first one, that is at low temperature, we get an alpha product, that is 1 anthracene sulfonic acid, and when it is carried out at a high temperature, we get 2 anthracene sulfonic acid. It is nothing but a beta product. So similar as we have seen in case of an naphthalene, that at high temperature we get an beta product, at low temperature we get an alpha product. After that, oxidation of anthracene, and oxidation it takes place at 9th and 10th position in presence of an sodium chromate with acidic condition. And after that reduction, so 9th and 10th position again it has been reduced, and this 9th and 10th position they are reduced with sodium in ethanol or by catalytic hydrogenation using padallium as a catalyst. After that, we have seen reaction and synthesis for phenanthrene. So phenanthrene, so the first synthesis method we have seen, that is Haworth synthesis method. The naphthalene it is reacted with succinic anhydride and followed by subsequent multiple steps to give phenanthrene. After that, from post-Scher synthesis, orthonitrophenyldiene, an acetate derivative of benzoic acid in presence of an acetic anhydride, gives phenanthrene with multiple steps. And after that, we have seen some reactions of phenanthrene. So the first reaction we have seen, that is halogenation. So at 9th position, chlorine has been substituted. We get 9-chlorophenanthrene. After that, in presence of an AlCl3 at 0 degrees Celsius with acetyl chloride, so this is nothing but an Friedel-Crafts acylation, we get a product that is 9-acetyl phenanthrene. Acetyl group it has been substituted at the 9th position. After that, nitration, so similar way in case of a nitration also we get a product at 9th position, that is 9-nitrophenanthrene. And after that, oxidation with sodium chromate gives 9,10-phenanthrequinone in presence of an H2SO4. And beyond that, we have also seen some uses of this phenanthrene and naphthalene. Most purposely they are being utilized as a dye, and also we have seen that there are some derivatives of anthracene and phenanthrene in case of an glycosides, which are having a multiple action depending on what type of an substitution does they have on an glycosides. And in case of many drugs, phenanthrene has remained as an basic moiety, as we have seen in case of an cholesterol, or in case of an morphine, or in case of some alkaloids.